When you tap Buy on your phone, the physical object you're looking at translates into a digital blueprint that a server can easily understand. This is a strict set of instructions that tells the computer exactly where to find your name, your address, and your payment details so it can process the order. Back in the early days of computing, if you wanted to change that blueprint, like adding a second phone number, you had a simple choice. You'd wait until everyone was asleep, turn the entire system off, update the files, and then switch the machines back on. But today, there is no off. If a global store shuts down for a few hours at midnight in New York, it's cutting off customers in Tokyo who are trying to shop during their lunch break. Our banking, shopping, and social apps are expected to stay awake every second of every day. Because we can't just flip a master power switch, engineers must find a way to swap out old code for new code while thousands of people are actively using the system. It's the digital equivalent of trying to swap out a plane's engines while it's cruising at 30,000 feet. To keep the lights on during an update, engineers don't change everything at once. Instead, they update the system one machine at a time. They give new instructions to one server, make sure it's working, then move to the next. This means you have two different generations of software working together on the same job. Traffic is being sent to both the older machines and the newer ones simultaneously. This is a huge shift from a developer's personal computer, where everything updates in an instant. In the massive networks that power the internet, change happens in waves, and those waves take time to move through the system. There's also the issue of memory. You can replace a piece of code in minutes, but the information sitting in a database might have been written years ago. A brand new server will frequently be asked to read a customer profile that was saved by a much older version of the software. Computers are incredibly literal. They only know the rules they were given. If an old machine and a new machine try to share a piece of information they don't both understand, the gears of the system can lock up. Without a plan for how these two generations speak to each other, the entire network will hit a contradiction it can't resolve and stop working. Let's look at a real-world example. Suppose a team is updating a payment app. They want to add 2 new slots for information to every receipt, a security token and a total for rewards points. A server running the brand new software reaches into the database and pulls up a receipt from a customer who shopped 6 months ago. That old receipt is smaller. It doesn't have those new slots for security tokens or rewards points. To prevent the system from panicking, the new code is taught to be flexible. When it sees those missing pieces of information, it doesn't crash. It just assumes the value is 0 and carries on with the transaction. This ability for new code to safely handle old data is what allows a modern system to survive contact with its own history. But the information also has to travel in the other direction. Imagine a user makes a purchase today, and the new server sends that updated, larger package of information to an older server that hasn't been updated yet. The older server only knows the old rules. It has no idea what to do with the new security token. To stay online, it must recognize the parts it knows and safely ignore the rest. The real danger happens when that older machine needs to make a small change, like updating a shipping address, and then save the whole file back into the database. If the old server isn't careful, it will save the new address but drop the pieces it didn't understand, like the rewards points. By hitting save, it has just permanently erased the new data it was supposed to be protecting. If the software isn't taught to hold on to information it doesn't recognize, a routine update can accidentally become a tool for destroying your database. To avoid these digital accidents, engineers follow a few golden rules. First, any new piece of information you add should be optional. Second, you can never change the basic meaning of the information you're already storing. Third, you must never delete an old rule that the system still relies on. And finally, you must make sure that even your oldest machines are taught to carry new information, even if they don't know what it's for yet. These digital rules actually mirror a physical solution from the 1800s. When railway companies finally decided on a standard width for their tracks, they faced the exact same problem. They couldn't just stop every single train in England to move the rails. Instead, they built a third rail alongside the original 2. That third rail acted like an optional piece of data. It allowed the older, narrower trains and the newer, wider trains to use the exact same path at the same time. No one had to wait for a total shutdown. The transition happened gradually, over years. Whether you're dealing with steam engines or digital payments, the secret to a safe upgrade isn't a sudden replacement. It's designing for a world where the old and the new can live together. Back in our payment system, the update wave finally synchronizes across every machine. The last of the older servers are brought up to the new standard, and the entire network is finally speaking the same language. Because the team followed these safety rules, no information was lost, no servers locked up, and not a single customer saw an error message while the engines were being swapped out. This careful planning is what allows the massive systems we rely on to grow and change every single day without ever having to turn off the power.